Okay, welcome to the lecture 22 in this classical mechanics 1 course. Today I will take a tutorial class. So, we will solve certain problems illustrating the topics we have learned in last few classes. Before that, let me recap what we were doing in last lectures. So, we were learning symmetries and conservation laws. We have seen that for if your system is invariant under certain transformation, that means if your system has certain symmetries, then there will be a conserved quantity. We have studied for translational symmetry of space, time and rotational symmetry. Also we have seen the scaling symmetry of the theory, and we have found their consequences. So, there is a theorem in quantum generally taught in the quantum field theory, that Noether's theorem, that says that for each and every continuous symmetry you will have a conserved quantity, and the charge corresponding to that conserved quantity will generate that symmetry, and it is also true vice versa. That means, if you have a conserved quantity, that can be related to a symmetry. So, we have with examples we have learned, and in the last class, towards the last class, we are discussing about the virial theorem. So, in virial theorem we found that if you have a motion in a finite region of space with finite number of particles, then the long time average, which I denoted by this bar, of kinetic energy is given by minus half time f I dot with r I sum over all particles 1 to n and its average. So, this was the virial theorem, and f I is the force acting on the ith particle, r I is the position vector of the ith particle, and their dot product and sum over all particles will give you the average kinetic energy. This average is long time average, that means you have to consider for sufficiently long time. We have proved this theorem, and as a consequence we are discussing. So, we found that if you have a potential conservative system, that force is obtained from a potential that del u del r I, and this u is assumed to be a homogeneous function of r I of degree k, and the kinetic energy T is assumed to be a quadratic function of velocity, then we will have the average kinetic energy of velocity. Then we have seen that this virial theorem says the average potential energy will be 2 by k plus 2 of the total energy, and average kinetic energy is, we proved this results in last class. Okay. And towards the end I was little bit in hurry, so that is why I am repeating this part. So, now suppose we consider few examples. Okay. For example, if you have a harmonic oscillator, for example, if you have a simple harmonic oscillator, that means potential is like half m omega square x square in one dimension. So, you can say k equal to 2. So, for simple harmonic oscillator you find u bar is E by 2 as T bar. So, this we known result that kinetic energy average and potential average, they are equal and half of the total energy. Then we discussed that for a Kepler's problem. Kepler's problem, that potential is proportional to some alpha by r. So, k equal to minus 1. So, if k equal to minus 1, u bar will be 2 e and t bar is minus e. So, apparently this looks a contradiction, because kinetic energy, average kinetic energy is minus e. This does not mean that the kinetic and average kinetic energy is negative. So, it does not mean negative. Q, why? Because this is a bound state problem, Kepler's problem, and the E is always negative. So, E is always negative. So, total average kinetic energy is positive, and the average potential energy is negative. Okay. Next, we consider another example. Suppose you have a potential. Suppose you have a potential U proportional to alpha by r square, that k equal to minus 2. Now, what will happen in this case? That we were discussing towards the end, and we could not finish. So, in this case, you can see clearly that potential energy and average potential energy and kinetic energy term has a factor 1 in the denominator, k by 2. So, when k equal to minus 2, denominator vanishes, and this will leads to the divergences, that leads to the infinite. So, what is happening here? Remember, when I make the statement of virial theorem, I clearly says that motion has to be in the finite region of space. But when this potential, the motion is not motion of the particle is not confined to the finite region of space. That means, for this case, virial theorem is not valid. Virial theorem is valid for when the motion in the finite region of space. Okay, so this was the discussion regarding the last lecture. Now we will move to the tutorial class, and in this tutorial class we will consider several problems. So, let us start with the first problem regarding the Lagrangian and equation of motion. So, find in this tutorial class, so problem 1, so find equation of motion for the following Lagrangian. Lagrangians. So, two Lagrangian I will consider. So, first one is that if L is for a many particle system, and it can be defined as sum over I mass of each particle, then xi dot square plus, let us write or minus g sum over I and sum over j, which is not equal to I, and then xi minus xj whole square. So, the region for considering these two Lagrangian, I will just explain. Let me write the second Lagrangian also. it is in vector form. So, r dot vector plus some constant vector a whole square half mv square type of term plus b dot r whole square plus c r dot r. Suppose you have this Lagrangian. So, the reason behind of considering this Lagrangian, that from my experience of teaching, I found that student has difficulties in when the Lagrangian is given for many particles in the with the summation and with the vector notation. So, that is why I want to consider these two problems. So, this is difficulties level is that to finding the differentiation when you have many particles in the case 1 and when you have a vector in the case. So, that is why I choose these two problems to emphasize this. Okay. So, let us consider the solution for this solution. So, when you have a summation in your Lagrangian and some quantity, when summation is involved, you have to differentiate with respect to some variable which is not some index you have to choose which is not appearing. So, for example, let us find the equation for the first case. So, case 1. So, let me write case 1. The equation for xk, because I and j variables we are using. So, we will consider the equation for xk. So, let us differentiate del L del xk dot. Why I am choosing xk, the different variable which are appearing in the apart from the Lagrangian, that will be clear. So, first term will be half, then sum over I equal to 1 to n, because depending on number of particle, the summation, all the summation is from 1 to n, n number of particles. Okay. So, mi is a constant, so it will not be differentiated. Xi square will be differentiated to xi dot, and then xi dot will be differentiated with respect to xk dot. So, this will produce a ik term. Okay. And you can see there is a summation over I and there is a Kronecker delta ik. So, the summation will remove and it will be mk xk dot. Okay. So, this is the technique one has to use when you have a sum over things. Now, the second term is a little bit more complicated. So, this is straightforward. That is why I use with a different level xk dot. So, such that there will not be any confusion. So, when I perform the sum with the Kronecker, this Kronecker delta, I will be replaced by k. Okay, good. So, now let us consider del x del xk. Okay. So, first term is independent of the xk, no x dependent. So, second term will be minus g, then let us keep the sum I equal to 1 to n, j equal to also 1 to n, I not equal to j, also this condition is there. Then if I differentiate xi minus xj whole square, it will give me 2 xi minus xj times the differentiation of this quantity. If I differentiate xi, it will be delta ik minus delta jk. Okay. And now it's you will take little, there are a delta function and two summations. So, one summation can be removed, and so let us simplify term wise. So, first term minus g and say I remove the I summation by using delta ik. So, I will be replaced by k. So, j not equal to k, and for 1 to n, and you will have 2 will come out, and you will have I will be replaced by k. So, x k minus x j, and this is the first term. Second term, there is already a minus sign, there is a minus sign outside. So, it is plus, and then 2 g will be as it is. Now I will perform the J sum with using this Kronecker delta. Okay. So I sum will be there, I not equal to k 1 to n will be there, and then it will be j will be replaced by k level. So xi minus xk. Okay. Now you can see that these two terms further can be combined, because this is xi, the dummy variable summation I can remove to I, then it is xk minus xi, here it is xi minus xk. So this will be 4g times sum over I not equal to k 1 to n xk minus xi minus xk. Okay. So this will be the result. So one has to be careful while doing such calculations. So your equation of motion will be mk xk double dot, because you have to differentiate, and this is minus 4g sum over I not equal to k will be 1 to n xi minus xk equal to 0. So this is the equation of motion. Okay. So this is the first type Lagrangian, where you have to be little bit careful. Now let us consider the second type Lagrangian, which has involved the vectors. So you remember the Lagrangian has half m r dot plus a vector whole square plus b. So let us you can break this Lagrangian in components and you can do, but that will be little bit lengthy algebra. So what we will do, we will directly differentiate with respect to vectors. Okay. So so case 2. So it will be, so let us differentiate with respect to r dot, okay, vector. So remember, I am differentiating a scalar quantity with respect to a vector. So I expect my right hand side should be a vector. So that is the only problem you have to keep in mind. So it will be half m. So if I differentiate, it will be half m will be as it is, then 2 r dot vector plus a dot vector will be there, and then r dot vector will be differentiated. So that's all from first term. Now what in the, there is also a velocity term in the last term, c term. Okay. So it will be, now you have to be careful, r dot vector dotted with vector this, and you are differentiating with respect to r dot vector. So this term will give you a c r vector. Okay. So when I differentiate with respect to vector, right hand side will be a vector, because L is scalar. So this is the attention you have to pay. So that I want to convey to you. Similarly, when you differentiate del L, del with respect to R, you will get, see where R is appearing, R vector is appearing in the middle term and last term. So B E dot R whole square. So if I differentiate with respect to R vector, it will be 2 B dot R, and then the thing will be differentiated with respect to R. So it will be a B vector. So this you have to be careful. Plus the last term, it will be a C R vector dot. Okay. So equation of motion will be now will be m ddt of r dot vector a vector plus C r vector minus 2 b dot r times b vector minus C dot C r vector. Okay. Okay. So this, let me simplify for you, m r double dot vector, and a is constant. So when I take a time derivative, it will not survive, and then C r vector minus 2 b dot r with B vector and minus C R C R vector. This is a dot missed here, so it will be a dot. So C R vector. So there will be a cancellation of this term. So you will have M R double dot vector plus 2. Nay, this will be minus because there is a minus. To 0. Okay, so this is two example where student has difficulties. So I emphasize this. Now let us consider the next problem. So this is not directly related to the tutorial class of this, because this is of the earlier tutorial class, these two problem, but let us move to the problems related to the conservation laws and symmetries. So problem 2, what are the conserved quantities? What are the conserved quantities in the system described by the Lagrangian? Let me give you the Lagrangian. It is Q1, Q2, Q3, 3 generalized coordinate, then Q1 dot, Q2 dot and Q3 dot. So 3 generalized coordinate, 3 generalized velocity, no explicit time dependence, and let me write the Lagrangian explicitly. Q1 dot square, Q2 dot square plus Q3 dot square plus or minus whatever you want, Q1 square plus Q3 square. So what are the conserved quantities? Now if you solution, so if you look at the Lagrangian carefully, you will find there is a cyclic coordinate. Q2 is not appearing in this Lagrangian. So Q2 is cyclic. So del L del Q2 is 0. So implies momentum conjugate to Q2 will be conserved. Okay. So momentum conjugate, so P2, let me write P2, which is del L del Q2 dot, by definition will be Q2 dot. So Q2 dot, I have not used any mass, okay, no problem. So this Q2 dot is a conserved. Okay. Okay, good. Now there is T is also cyclic. There is no time terms. So no explicit time dependence. So we can safely say that total energy conserved. Okay. So two conserved quantities we have found, momentum conjugate to Q coordinate and the total energy. So these two are conserved quantities. So this most of the students generally find these two conserved quantities, but you have to look for another quantity. You have to check whether any other quantity will be conserved or not. for example, related to the rotational invariance, whether this Lagrangian is invariant under any kind of rotation. So, in last lecture when we discussed the isotropy of space and rotational invariant, I mentioned that when two coordinates will be there with the same like q2 and q3 in this case with the same coefficient, there is a possibility of rotational invariance. So, if we consider a rotation, in this case consider a rotation about q2 axis. Okay. So, if you consider a rotation about q2 axis, that means your q1 and q3 coordinates will change, they will rotate by, they say if the rotation angle is cos theta, so cos theta sin theta and minus sin theta cos theta times q1 and q3. So, under this rotation you can check q1 square plus q3 square will be q1 prime square plus. Okay. So, if you have a rotation, you have to check whether there is any rotational invariance to this system or not, and we can very easily see that this Lagrangian density is invariant if we perform a rotation about q2 axis. For example, under q2 axis there will be changes in q1 and q3 plane, and by this transformation. So, and you can see that this q1 square plus q3 square will be q1 dot square q prime and q3 prime square. Okay. So, let me write this because there was some mistake. So, q1 prime square and q3 prime square. Okay. So, what happened that we find that q2 rotation about q2 is symmetry. So, so there will be the q2 component. So, angular momentum component along q2 direction will be conserved, and that you can write that q1 p3 minus q3 p1, because this will be the if you write m equal to r cross p, then you will have I j k and r cross p. So, r is like your q1, q2 and q3, and corresponding momenta is p1, p2, p3. So, j component, that q2 component will be q3 p1, q3 minus p1. Okay. So, this quantity or minus of this will be conserved. So, we can find from here will be conserved. So, when you have to find the number of conserved quantities in a system, you have to carefully look for the what are the symmetries does it has. So, in this particular system we find that this Lagrangian is symmetric under time translation, Lagrangian is symmetric under q2 translation because there is no q2 appearing. Okay. And also if we perform a rotation about the q2 axis, then it is also invariant. So, there will be 3 conserved quantities. So, any system given to you to find conserved quantities, you have to look for the symmetries. Okay, maybe this is time is over for this lecture. So, we will continue the tutorial class in the lecture 23 also. So, bye for now. So, we will continue tutorial class in the next lecture also. Thank you.